So today I'm going to talk about this, in principle, introduction to this idea of representation learning. But before that, I think it's, in my opinion, it's very good thing to know about this Fourier analysis, because I think these are very, very fundamental issues, and then you can track them back to 1801 or something like that. And then you see these recent developments, like in these convolutional neural networks, are like a bit of improvement of these old concepts. And then, for example, you see that this gradient descent is like 300 years old. If I'm not wrong, yes, almost. And then you see these kind of regressions that I told you is, in principle, the concept is again 19th century, beginning of 19th centuries, and then these ideas also from that time. So it's interesting if you look at them like that, then in principle it's like a beginning of Big Bang. So you can go in that time, and there are lots of diversities. If you can catch them there, then you can come further. Otherwise, if you start from the end, then in principle there are lots of libraries, lots of algorithms about anything. So nowadays called, for example, there is one method is called GAN, Generative Adversarial Neural Networks, which is a very powerful method and also idea. And then nowadays there are like GitHub pages called GANZoo. And when you go to GANZoo, you see there are lots of new libraries and new algorithms with a lot of small improvements. And if you start from there, it's like you start from the leaves of a tree. And I think what I'm interested to do is, in principle, to find what are the roots. So if you get the roots, then you can read them later on. But of course, if you want to really work with them, you need to, at the end, use the state of the art. It is not an excuse to say, okay, just for example, if you start with Fourier Transform, that's enough for you. You don't need to know what's going on in deep learning. I think it's wrong also. And it's not a matter of resistance. So I think I would next week I will talk about this convolutional neural networks, but I think for me this is the best way to go to the convolution through Fourier analysis. So if first of all, the difference between this kind of Fourier analysis with the classical, let's say, the other methods of transformations like PCA, is that here we usually talk about the so-called homogeneous data sets, like signals and time series, and then videos, text. And these are called homogeneous data set because, like pixels in a picture, these pixels are from the same context. And if you don't have this condition, for example, if you want to predict the price of this laptop, then you say the size, weight, CPU, RAM, and so on. These data points are not homogeneous, so you cannot replace them. But with the pixels, you know that there is another level on top of the pixels. For example, you're looking at the face of a person in the picture, then in principle these pixels are all together helping. Classically, these pixels become one dimension, but we know that the real dimension is not there. But when you have heterogeneous data set, is when you have a systematic way of data collection in a machine and so on. This is when you have clearly different contexts, like what I told you, weight, size, price, and so on. These are not easy to combine. So, but this, most of the, I'm very happy, I don't know, a lot of problems in many fields can be handled by this kind of homogeneous data set. Like you can think about any application, and then you can, I will show you later, to convert them to a picture, for example. I mean, as for example, also Lucas mentioned this. So then, when the moment you convert a data set to a image-like data set, then you are in a homogeneous data set. So then you can use a lot of methods like there. So Fourier analysis is when I think I will mention this later on again, but it's at the level conceptually at the level of PCA. Remember, PCA was a kind of orthogonal transformation of the data in a way that the new bases are not overlapping, so it means that orthogonal, they don't share any information and so on. And here in Fourier analysis also you want to do it for signals. There you do it for this high dimensional data set. Here is about signals when you have time series, for example. Then in principle you're caring about the whole experience. And then you want to decompose this signal to a set of orthogonal patterns. So the whole idea is that instead of having these orthogonal patterns being in a time domain or in a geometric interpretation in a kind of is a vector in the space. Here you are dealing with a harmonic or cyclic pattern. So instead of, you can build a signal or reconstruct a signal with a lot of cycling patterns, right? These are like sinusoidal functions. You will see it immediately. So before that, I would like to mention that there are lots of main problems, and I mean these are very, very fundamental problems. I told you already about this. Usually, that observations are homogeneous, which means that we like pixels of image or sequences of values in sound, signal, and so on. And usually, we are looking for something on top of these observations. This is the case. Like when you look at the picture, if you show pixel by pixel as one dimension, you lose a lot of context. But when we look as human, when we look at the picture, our vision system is working in a different, because we say, okay, that's this kind of person in the picture, or this is about that, what is the message in this sentence, and so on. It's not just about elements, it's about their relationship, and it's about topology of them, and all together they create this pattern. So, and all these methods are developed in a way to capture this notion of invariances. With categories of interest, for example, we have translation invariance. I told you about this a lot. For example, if you have a picture and I have this wallet here, and then I'm moving here, still you see that, right? But if you don't have this, this is a translation invariance. Everything is the same, I'm just moving this in this frame that you're observing me, right? So if you literally take the pixels, you don't capture this information because it's somewhere there. And then if you imagine just compare pixels by pixels, there is no way. So you need to understand that there is some invariances which is moving in this space, and then I want to capture that. So then sometimes you have rotation invariance. This is one of the hardest one, and this is the same thing. 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 But pixel-wise, again, they're rotating. So imagine you have a graph, and then graph in principle is dimensionless. So if you show a picture of a graph from this side, or the other side, for us it's like, okay, it's the same graph, because the topology is the same, right? But then you need to find a way to capture this kind of differences. And the question is that the main problem is that if you don't do it, you need a lot more data sets. Because then if you want to predict a wallet, for example, you need to have all of these data sets. Otherwise, your model is poor. In principle, you need a lot of more data, and this is the curse of dimensionality. But you realize that there is something which is rotating. Actually, you have only one dimension, which is this angle. Then you just say, I can learn it by a linear regression in the dimension, in a high dimension that this data lies in, so that you capture the meaning of angle, for example. Then in principle it becomes easy. If you have this one or this one, you can interpolate in between. Otherwise would be that you just interpolate the pixel values. It's extremely hard. It's not working at all. And then you have scale, small, and so on, and then you have deformation. So you have different types of data set also. Another important factor is hierarchical representation or compositionality. So these are really important things that I think nowadays empirically works with deep learning methods. And hierarchical representation or compositionality means that you should get what is this word hello, and then you say hello, good morning, or I am going. So then you should understand I am going. So then you go to another level, I am going to, you can make it a part of another part to say I'm going to school, I'm going to restaurant, I'm going to this, and so on. So then you need to first of all understand each of them in one level, and then on top of that you learn other things. And then for example, imagine in a graph also, I'm just connecting to your field, is that you need to understand similar local similarities, and then you, based on this local similarity, they are getting connected, and on top of that you see something emerging which is similar. Or for example, or face, you can say I can build a model, because it's really hard to detect a face detector easily. You just say, what if I learn a model that in an abstract layer, in the first layer, start learning what are the edges in the picture, because these are the most informative points, and then on top of that I want to say where are the eyes. So then you understand that this is called eyes, but nobody labeled it in advance. You learn it, And then you learn that eyes are always in principle coming with this, which is called nose, and then with these two. So this is compositionality. So if you can learn them separately, then because of this combinatorial effect, you can do a lot, because then you can combine them. So that's the whole idea. And the opposite to this is when you don't learn it, and then, for example, you have this classical semantic or syntactical rules in language, for example, that people say, what if we can learn or we can hard code these rules first and then write the program? And this has been the original idea, to write logical systems or expert-based systems and so on. But most of the complex things, it doesn't work. So with this machine learning, you always want to capture these things, these invariances, and also to learn this hierarchy. So, but anyway, I think it's good to start from the basics, like what we did with linear regression. Usually we don't use linear regression, but if you get the concept, you go next. And here I think Fourier is like that. So for example, this is translation. You can have the same signals, and then but they have time delay, right? So if you here again compare them pixel by pixel, they are not similar. But if you get the understanding of this translation, then you're good. Or deformations. These are all the same digits, and if you go pixel by pixel, it's extremely hard to find, right? And then this is also scale. So these are, I think, another way to categorize, or I would say categorize the methods that have been developed over the last 100 years or 50 years ago is like based on this. There are lots of different methods that they can handle some part of these features, like scale invariance. And then there are some methods who can handle this rotation, but not all of them. So also this could be a way to try to make kind of a guideline for yourself how they are working. So then now Fourier analysis is among the most fundamental methods in this field, I would say, and then developed in early 19th centuries. And it's about interplay between time and frequency domains. And you can see here, essentially this is important. It says it is possible to represent any integrable function as a linear form, a linear sum of sinusoidal functions with different frequencies. So it's like PCA, but in time. Or in principle, in PCA, you can reconstruct your data set with a set of orthogonal bases. Here, your bases are sinusoidal functions. So in principle, they have time in their themselves. So for example, if you want to, I don't know which model was that, sorry, but then for example, if you want to get this pattern, you can see that this is just the sum of these different cycles, right? And then there are theory that you can represent any function as long as they're integrable. Or for example, this one, you see that they're working. And more maybe interactive version would be like this. I think this is really beautiful because you look at this in reality, and then you don't believe that you can reconstruct it. And this is like most of the other things. Like if you remember, we had these two diagrams. One side was a line, and the other side was a red line, and then the other side was lots of small dots. You remember this in the first slides, in the first sessions about this rationality, that you have observations and then you always reduce it to lines. And PCA you are doing that, and in Fourier you are doing that. This is called in principle idealizations, right? You reduce these complex observations to, or reconstruct it or decompose it into this idealized form. So in principle we say what you observe is the sum of these three harmonics. And then you can, for example, play with that. Make it faster. So this is for the cases that you know the function already, but in reality we don't know the function. That's the main problem. So it becomes data driven. So what I explained to you is like this, and this is called Fourier series. It's like Taylor series and so on, but it's conceptually different. So if you have this function, and then you can reconstruct it by these cyclic patterns like this, and then you can get it. But in reality you need to know these functions in order to calculate these derivatives and also integration. But in a data driven way, we just have the data, we don't have the function. So there are methods, and this is called, for example, discrete Fourier transform, that this is in reality happens. that you do this reconstruction only based on this matrix formats. So I don't know if I have it later. Okay, I have it here. Sorry. So in order to go further, I think it's important to tell you about this Euler formula, or this complex exponential, that you can represent this combination of this complex vector, that the real part is a cosine function and the imaginary part is a sine function, with this complex exponential. So it will help us a lot in terms of computation and symbolization. So yeah, you see that it's just to show you that they are the same, so you believe me, I think it's fine. So you will see that if you have a cosine functions, and if you take the real part of this complex exponential, it will overlap. So it's the same thing, right? Because the magic is in this I number. So DFT, or discrete Fourier transform, is very simple. So somebody came up with this idea that if you build this matrix, and if you multiply your vector or observation to this, it decomposes them and takes them to Fourier transformation, frequency domain. So compare this with what we had before with like PCA. In PCA also you build this matrix in a way that it transforms your data in a new space, and that in new space the bases are orthogonal. Here also the bases are orthogonal. So in principle this means that each row and also each column, if you multiply them by each other, the dot product is 0. This means that this is like this always, right? If it's like this, they have overlaps. Here is always like orthogonal, like PCA. But important thing is that in principle here is not data driven. It's just what is important here is just number of observations, and it depends on the number of points that you have. So that's the limits in the signal in the sampling theorem. So the idea is that now if you build this, and this is called Fourier transform, this matrix, you see there's a kind of exponential function and the power based function, then you just, this is omega, and then you replicate this like that. If you build this for any size, then you have your Fourier transformation, or discrete Fourier transformation. And this is what we had in PCA. So one important factor in my opinion is to know that now we are talking about the whole signal as one data set. So they are conceptually the same, but in the PCA, each of these data points are like independent. And that's the difference. Here you think about relationship between these points in time. This is topological, and here you think about the geometric, and it's a geometric way of looking at the data. So you have points, but algebraically, or linear algebraic way, is both of them are matrix decomposition, or both of them are linear transformation, because this linear transformation, I told you, when you have this matrix, when this matrix is a linear operator, which means that it takes your data from here, takes it to there. It can't do more, and it's always linear. This is linear transformation. And then here you do it on time, you decompose it on time to several main functions, and again what you care about is what are the coefficients, because it's like later you will see that you build these basis functions like PCA also, and then for each new observation it tells you how active is these base functions in that. It's like you have pair of glasses, and then by different pair of glasses you have different views to the world. And these stationary waves in these idealized patterns, they look at your data from their own point of view, and then they say, okay, I see it there. The next guy says it's there, and these are different frequencies. So in principle, if you have the same signals, in principle stationary signals, if they are exactly the same, also if they have translation in time, it's okay, but they get similar activations in the frequency domain, because the same signals get activated. So then you say they are the same, but if you compare them one to one, they are not, like the case I showed you about. So you build this, and I really suggest you to build this also, write it down, it's like a NumPy array, and then let's see how it works. So further comparison to PCA, at the end I will come back again here. Both are linear transformation, both have orthogonal bases. Let's call them, or call it, crystallized bases. These are crystallized because they have absolute symmetry, they have no information sharing, and you will see that later. I mean, we'll also discuss it in deep autoencoders. When they have overlaps, it gets better always, when you have this redundancy. And I think it has also a philosophical meaning for us also. When you're absolutely rational about something, you might miss a lot also. So you miss a lot of flexibility, you lose a lot of that. And you will see that this is exactly the case in, for example, convolutional neural networks, or this is exactly the same case in these deep autoencoders or deep neural networks, because you gave up these idealizations. And it's like you really don't want to know what are the steps, but because of that you get better results. And I think that's the whole problem of machine learning and expert. I would say the way usually experts don't like machine learning is here, because experts want to know what are the steps, and here machine learning says, I build a specific custom steps for your problem. And then you get puzzled, because you just say, no, I want to know what are the steps. But then they say, yes, if you want to know what are the steps, then you are in this crystal world, because they're idealized. And when they are idealized, it's understandable. You say, okay, I understand frequency, I understand time, but what is in between? Nobody knows. So if you have n4, you can build these spaces. It's like this, and that's it. You can now multiply any signal to this, as long as if they have the range of 4, right? Then you can get what you like. So I hope it works. Now, for example, now we have 256, and look at these harmonics. This is the real part. When it's 0, you should look at the first row is always 1, and the second part, imaginary part, is 0, right? This is basis 1, and if I use basis 2, is this 3. You see the frequency is changing. So these are like filters. Now from now on, when you want to observe something, you put this filter in front, and then you see which one hits, and you say, okay, this is active. So because they are timeless in principle, it doesn't matter when this pattern happens in time, they get activated. So then also you can see that different patterns emerges on top. You see, this is, you have in principle 256 filters, and in between you see also some crazy patterns emerges also. So at the end you have very high okay, it's symmetric, sorry. At the end it goes back to the, so in the middle is the best, the maximum frequency. So another way to show it is like this. You see, this is only for, I think, 4x4. You have this kind of pattern. It's simple, like again, like PC, and each of them are, if you multiply always the combinations of each row or each of them together is always 0, dot product, and also this sine and cosines are always 0. So this means that you have covered the whole space. They have no redundancy in terms of information. And this is, I think, here you see that if you multiply them, that product is always 0. So now what happens? Now if you have this data set, if you use this filter, just multiply your data to that, it gives you this. So this tells you in the frequency domain, for this signal, only 2 numbers, which is symmetric. In principle, you can take one of them. 2 numbers are activated, which means that this data is being produced by this frequency, right? So in principle, if you have 2 signals with a delay in time, if you compare them in time domain, they are not similar at all. Like this is what I told you. If this is the same thing happens everywhere, this will be captured by one of these waves. And it says it doesn't matter where it's at, as long as it doesn't change. But if you change it like this, or if you open it, then it's another story. So this is what I told you about, right? And you have the time domain, you build these filters, and these filters are in principle not data driven that much. They're idealized based on frequency, and the number of filters is based on the number of observation, and it tells you, and then you simply just multiply that, and at the end you see that number of the mathematics behind our operations are super basic, just one-to-one multiplication and sum over it, and if the value is high, it means that there are some similarities. So, and in principle you don't use DFT because in practice, sorry, not in principle, in practice, because they have time complexity. If you increase the number of size, the number of bases increase, and so on. And there are methods for making faster. For example, the most common one is a FFT, or fast Fourier transform, and this is already implemented in NumPy. So you don't really need to implement it. So you see that I'm doing the same data set with two approaches, and they have the same result. So I'm preparing here two signals, sample signals, everything the same, from some except some translation in time and some random noise. So this is your observation. And then when you do this Fourier transform for each of them, you see that they are similar. So that's always like that. So we just want to capture this information, and you will see that Fourier analysis is not enough for everything, but it still is super powerful, and it's not machine learning because it's there. You just need to implement this. For example, if you don't want to use machine learning, if you want to analyze some pictures or something like that, immediately start with Fourier analysis. So it gives you a lot of information. So in principle, for example, if you want to train a self-organizing maps or do clustering, first convert them to the Fourier analysis, to the frequency domain, and then take this data as a data for your next step. This is called feature engineering, because you don't learn them, you just engineer them. So also you can reconstruct the signals. So if you simply use none of them, so you remember for this PCA I did the same. You move to the new space, and you come back with only few of them, which are most informative. And then you expect that what you get in the second step is not the same as what you get. For example, it's like a noise reduction, or some of the information are missing. Here also we do forward and backward. But every time that we go forward, we just say for the backward use few of them, not all of them, and see what happens. For example, this is again this linearity, right? So 5, 6, please. So now we see after a while they're getting more informative, and then with only 30 frequencies you get the pattern, and then you see at the end you can reconstruct the whole thing. So what is this good for? For example, you can do it for denoising, because noise means high frequency. So I have this data set. Now I can do forward, and this is Fourier. So he tells me that these activations are, in principle, you can get rid of them because they're not very important. These two are symmetric and also important. So what I do here is that simply I take those low frequency, and see it's just with 3, 4, 5 we do denoising. So this has been there. I think most of communication theories and all of these mobile devices we're using, they are using this kind of technology for many years. It's not something new. But you see how powerful is that? Just by change of your mindset, you go to another word, and then in that word you just pick those informative points, and then you come back, and then you are relaxed. And if you want to do this denoising in the time domain, it's a different story, right? You need to do local averaging and so on and so on. So at the end, of course, you can play with that in a parametric way to say, okay, how much noise you want to have, or how much smooth you want to have be your signals, and at the end you get everything, right? It's very slow. So you have the same. So you don't lose information. Again, I want to push you to that direction. Think about it conceptually, like PCA also is doing the same. And they are time-wise also. PCA is like 100 years later, but conceptually they are almost the same mindset. And both of them don't like noise. But I think in deep learning you realize that noise are really beautiful. Noise is important. Because noise means you say I don't like outliers. And you know that outliers are those good guys in principle most of the times. Or there are those who are changing the society, for example, not necessarily the mainstream. Here, conceptually, you see that there's a big shift. You can think about also about, I don't know, society and how nowadays the governments are set up and so on. So now in principle you can do it for 2D also, and you can do it for ND, but then it's not easy to visualize. Then for 2D means that you have two of these orthogonal decompositions, and then they get intersected. So here, if I say 0, then one looks vertically, and the other one looks horizontally. And if you don't use any of them, you have nothing. So you see that one is helping me like this, and this is a picture of, I don't know, 32 by 32, and this is like that. So you see, it creates almost anything. But it's very slow if you want to use it. So don't use it. Go to FFT 2 dimension or FFT in dimension. So you can always have these dictionaries. And then this is for me very essential, because later in deep learning you will realize that we learn completely random looking filters. And by that you get better results. And I think that's the achievement of 21st century maybe. I don't know, 20th century. Because you forget about these grids, and then you just go to another word, which is quantum, and it's not understandable. And that's why nowadays you have a struggle with this machine learning. People say it's not explainable, it's black box and so on. No, it's just another level. Here it's understandable because it's grids. And there with deep learning, machine learning, advanced machine learning, you don't understand it. But in principle you design it. It's not like something out of blue. So this is 3D, and then also you can play also with these edge detection things, and you see that how good is that. It's called low pass, high pass filter. These are old school things, but very powerful. So, oops. What did I do? Can you find the error? Yeah. Problem. And -6. Okay, we should change into something. How it works. Oh. Low is hard. No, the thing is that I was using another picture before and I removed it. Now I should change this. Let's do it first. No. Strange, huh?
If you comment the line 8.
Line 8.
Not because
That's right. Thank you. Yes, okay. Because it was reading another image which was smaller. So now if I use high frequency points as a filter, imagine you have this data set, it finds all of these edges. And if you use the other way, the low pass filter, it finds the context. So this is very important, how to get the edges, for example, right? So it's just a very basic way, but then you go to edge detection, open up a site-fit image, there are millions of methods. So I'm not saying necessarily you should use this, but I think it's important to understand that those edges are those areas that are like spike. So it means like they are like based on some high frequency pattern. And then when you get this low pass means that in principle you get those areas which are like flats. They're not changing that much. So what I do is like this, similar to this denoising thing, but I only use this high frequency or low frequency, and then by that you get this. But it's not in any way the best way, so you need to test many other methods if you want to do this. So effect of shift, for example, also is interesting. If you have this one, it gives you this one, right? This is a picture image of this thing, and then now I'm moving this to somewhere else. You see still more or less the same pattern. So this means that this Fourier analysis is shift invariance or translation invariance. So, and also I can do a lot of them. You see they have the same pattern. Imagine if you want to compare these points together, if you want to see if they are from the same distribution or not, or same particles or not. If you compare them pixel by pixel, there is no way. You need to go to the frequency domain, and then you see they're more or less the similar thing. So, however, it doesn't work for scale invariance, which is obvious. So, and then this is different. So then this will be introduction for why we need to use all methods. So another thing is that it always looks at the whole signal, which means that this Fourier, this idealized signals are based on a stationary frequency. What happens? What if in some part of your signal you have different pattern and then another part different? So in principle, you can mix this time and frequency together. And for example, there are many methods for that. For example, wavelets have been there for I think 50 years, maybe more, I don't know exactly, and many other methods. But in principle, these are like improvements of Fourier analysis. But in my opinion, there is a conceptual limit in these approaches, and as we can see, filters in Fourier series are just marginally affected by data. So that's the whole thing. They are not data driven. And conceptually, Fourier transformation is at the same level of, for example, polynomial regression, where the structure stops you a lot. So you just say, okay, what if I stop this mindset or thinking about structure about like these polynomials? Then you go to local linear regression, you go to this random forest and many other things. And here is the same. What if you just say, what are the fundamental assumptions in Fourier analysis? And I think when you ask questions about them, you are in a different world. And if you don't ask them, you can sometimes do small modifications. So the fundamental question has been always that if one can let the models learn the filters in coexistence with data. So that's I think what I have been always telling, and I think this is the main message of machine learning. And I think the main problem also I see many times, people use these powerful machine learning methods, but again come back and try to understand, which is a valid question, but most of them I think it doesn't work, because this machine learning gives you a greater capacity in a way that it introduces also a lot of more contradictory explanations. So if you want to know why, then you need to reduce it again to this style of thinking which is based on why. And here in machine learning is always about what. And this looks a bit scary, because you simply say, I trust this intellectual setup of machine learning, this gradient descent, objective functions, and then a great capacity of these models, and then let them learn. I don't want to know. With Fourier is not like that. In PC is not like that. You just want to understand. In linear regression also is the same. Now in medical industry, for example, many say we just use linear regression because it's explainable. But it's fine, because we don't want to use something which is complex, and that's also correct, because there are lots of other concerns, like these errors. What happens if there are some errors? Oops. Yep. So this is end of this part, and I think I thought it would be too much if I want to now bring this deep convolutional neural network, but I think it's good if you think about it a bit, and then next week you will see that how this convolution is in principle more or less the same thing, but then you just change this idealization part. You don't want to start with design features, you just say I want to learn them, and then you just say I don't care if it's just absolutely frequency or absolute time, you just say it could be in between. So another way, which for me was very unique way of explanation, is we are working with a group of other experts. Like this is one of them, Elias Zafaris. He's a quantum physicist, and he's working on this category theory and so on. And then we had this discussion about this Fourier transformation, and he gave me also another way of looking at this, which is, in my opinion, very interesting. And we can think about this, and he calls this something like this, as a kind of, it's called gnomonic diagram. One is time, one is frequency. So far what we have talked about, and this is I think most of these are called rational models, they're either in this direction or this direction, and here in between it's meaningless. Nobody can interpret what is that. So for example, when you have data from time, you can use FFT, and FFT is in this space is 90-degree translation, not transformation, translation of your point to this point. And then if you say what is 45 degrees, what is the corresponding matrix for that? Nobody knows. And this gives you an abstract view that where are we walking, you know? It's like, in principle, this is the whole 19th century science. It's just either this or this one. And then for each of them you build a lot of models, like this Fourier transformation. You say if they are based on this matrix, it moves you from here to there. But it's not easy to say, okay, what if it's 92 point degree, not 90 degree? Then the whole matrix will change. So then in principle, if you want to build the steps, you always have been building steps either in this line or this line, and it's like a small fraction of space in this circle. So first thing that you can ask is that in principle this tells you that if you do Fourier this FFT 4 times, you should be in the same place, which is not the exact case, but literally it works. What happens is that you have another z dimension, that when you do this and then you go to the first step, the amplitude of this circle, or the radius of this signal, is just increasing. This means that it's like with this Fourier transformation, and this has nothing to do with this classical time frequency, it's just a conceptual thinking. When you say Fourier transformation, which means it jumps off 90 degrees, and nobody knows what is in between. And when you do it, like it goes like this, goes that, but then over time it increases the circle size, and then it goes up. Now the question is that, then in principle, if you repeat this, like what we do in PCA deep neural network, in principle we thought that we get somewhere. But with this circular pattern, it tells you if you repeat, you are in the same place. Don't repeat it. So in principle, it's not also good for deep learning. So what I do is that, for example, now I take this data, and for 10 times I do frequency analysis, this Fourier analysis. So this is what you get. First time signal, second time frequency, third time you are in, again, time domain. So frequency domain, time domain, frequency domain, time domain. But then look at the amplitude of these signals. It's increasing in a crazy way. First time is between this, let's say 0 to 100. Next time is 0 to 30,000. And then next time the signal looks the same. And after 4 times, there is no shift. You see? If you normalize it, it's the same signal, which means that you repeated it, you're in another circle. And this has nothing to do with the concept of the sinusoidal directly, but it's about the concept. And now think about it, and I think this would be interesting, but I've never tested. This was very recent discussion that we have. What if we learn these angles? And conceptually nobody knows where is this space. In here it's called time, and this is called frequency, and we are used to it. We say, okay, we understand it. Time or frequency. And here is somewhere in between in life. And this is interesting. Now, what my interpretation for deep learning is that you learn that, and you don't restrict yourself or constrain yourself to be only 90 degrees jumps. You can say, let's play with that. So in principle, let's do it like this. So this is like 45 degrees, and then you say, okay, do 45 degrees, and then from 45 degrees go jump to 20 degree translation, and then another 50 degree, another 360 degree, whatever. This is like you start with randomized filters. You simply don't know where are you going, and every time you don't want to go to the same place. So then you do it, and then by the results, this is the learning part, you just say, now with this back propagation part, correct it, because I want to be there. I don't know how I got there, but I want to be somewhere else, like here, but I really don't know the steps, and that's the whole trick. And then this you will see this next week. For example, convolutional neural networks, in my opinion, are here, if I'm not wrong. I'm just, to be honest, I'm not sure 100%, but we can test it. So you have these jumps in between, which are meaningless in reality. You can't understand whether it's time or frequency. But then you just say start, and these are like, for me, each jump is like one layer in deep neural network. Then you just say random jump, random jump, random jump in the first step. And then you produce some results, and then you check the results. You don't care about the process. You just say, what was the result, what I was expecting. And then backward, you adjust these jumps. And next time for the new data, you again do that. And then when the network is converged, this means that you have fixed jumps now for these data sets. For example, would be interesting, I will do it maybe next week, train a neural networks for MNIST data set, and then try to understand what's going on in this space. Because what I think we can do, I'm not sure, we can reconstruct it from the amount of information we have from the time domain and from the data we have frequency domain. Now, okay, sorry, it's too speculative. But this is, I think, interesting. And then for me, this is extremely powerful, because then by that you just simply say Fourier transform. Yes, what is Fourier transform? 90 degree jumps from in this space.
But you would use the Fourier transformation to be a generator for the result, or
no, if you use Fourier transformation, it's like you're just jumping 90 degrees. Yes. And I showed you, with 4 jumps you are almost in the same location.
But you would use now one as an input and one as the output, and learn the steps in between.
Or no. In reality, none of them are interesting, because in reality you take this, and for example, this is your observation, yes, and you take this as your input for linear regression, because then you just say, I want to find if these two climates are similar, right? This is like temperature. But now with this deep learning, like what we did in PCA, we realized that it's not just enough one step. What if we take the output of the steps and then do it again and again and again? What this diagram shows you is that it tells you that it's not that helpful if you repeat Fourier analysis several times, because you end up in the same location.
So this would be like 1 times 90 degree would be one convolution, right? And then
yes,
1 times 90 degree another convolution.
Yes, but not necessarily 90 degrees.
40 degree convolution, let's say.
So my guess is that if it's 40 degree, it's already a kind of learned convolution. And in here you just decide the degree first, and then you build the machine that moves you from this location to another location. In machine learning, you learn it. I think
you learn the degrees.
Yes.
The
you learn the degrees, and I think if you represent it, if you can, I don't know how to represent it in this diagram, but if you do it, I'm not sure if it's meaningful. Because it should not be meaningful. It's just, imagine it's a kind of again combinatorial problem. Imagine you have 5 steps, and then you have, let's say, degrees. The jumps are 5 degrees, like 5, 10, 15, and so on. And then you have 5 layers, and then you say, let's say, from 0 to 90 degrees. So in principle, you have 16 possibilities in each layer. So then you say, I have 5 layers, you have 16 by 16 by 16 by 16 combinations of jumps in 5 layer deep neural network. And this gradient descent helps you to find the best based on your data set. So this could be an interpretation of that. I don't know. I know few people like in theoretical computer science are working on that. I really don't understand what they're doing, but I understand this. So yeah, I'm also
maybe when we think about the deep network, and like we always train it with an input and the output, right? So how do the different layers translate within each other to define these angles that they start, like they have a first layer, you start with an angle, let's say, then you go to the next, but they have to somehow interact with each other to get to that, right?
They are working together. Like here, you can also use the same. The output of one is the same as self-referential. You see that x1 is the same, and this is like any neural network. The output is readable for the next inputs.
Yes.
It's not a problem, but the problem is what is the matrix in the layer in between, because the arrows are the matrices, and here you just assume that you know. So here it simply tells you that you can't have a deep neural network based on Fourier analysis. I think this could be the first proof. It doesn't make sense to have deep Fourier analysis because you're in the same location. Yeah, I don't know how to test this with this, how to bring it here, because this is conceptual, and we only know maybe there's a way to have a parametric Fourier analysis, Fourier transformation, that I don't know. If you know that, then, for example, if you can parameterize this, if you can parameterize this to say that this is 90 degree, what would be that matrix for 20 degrees? Then maybe you can optimize. Maybe you can optimize the way people train neural networks, because then you have a meta parameter. You don't need to learn all the factors, and this could be amazing. But yeah, okay. So this was like, yeah, more just theoretical part, but believe me, these are the methods that nowadays are being used everywhere. So for fun, now I'm doing is that I'm crawling AutoScout dataset, because I want to see whether you can find similar cars by image queries, for example. Now you just say, I like this car, where are the other similar cars based on look, for example, in this, I don't know, 100,000 pictures in AutoScout. You know AutoScout, this website for cars, second-hand cars. So there you can easily use this, and so it's this size of code. You will see next week. You can get the code, clean your data, put it in the pipeline, boom. So now you have an app, in principle, that when you upload one picture of a car, it finds all the similar cars, and this is all about these colors, translation, rotation, deformations. And if you don't use these methods, there is no way to do that. You can only play with the color, and then it's not just the color of the car, just the overall color. Maybe the background is black, is different result. Okay. So now these concepts can go to graphs. So because graphs also are homogeneous, so you can do Fourier analysis on graphs, for example. And I think now these are the hot topics, I think, in these developments in this machine learning society, how to do these kind of things for non-Euclidean spaces, like a manifold, like a graph, that you don't have the whole space, but your data lies in a certain space, which I don't know myself very well how it works. So see you next week. Okay. Thank you.